Standard 9 Science and Technology. Chapter number 1 Laws of Motion. Motion of an object. Can you tell? In which of the following examples can you sense motion? How will you explain presence and absence of motion? 1. The flight of a bird. 2. A stationary train. 3. Leaves flying through air. 4. A stone lying on a hill. We see the motion of several objects every day. Sometimes we cannot see the motion of an object directly, as in the case of a breeze. Can you list other examples of motion besides those given here? Think about it. 1. You are traveling in a bus. Is the person sitting next to you in motion? 2. What do you take into consideration to decide if an object is moving or not? You have learnt that motion is a relative concept. If the position of an object is changing with respect to its surroundings, then it is said to be in motion. Otherwise, it is said to be at rest. Displacement and distance. Let's try this. 1. Measure the distance between points A and B in different ways as shown in figure 2. Now measure the distance along the dotted line. Which distance is correct according to you and why? Think about it. A. Sheetal first went to her friend Sangeeta's house on her way to school. B. Prashant went straight from home to school. Both are walking with the same speed. Who will take less time to reach the school and why? In the above example, is there a difference between the actual distance and the distance travelled? What is it? Distance is the length of the actual path travelled by an object in motion while going from one point to another, whereas displacement is the minimum distance between the starting and finishing points. Use your brain power. 1. Every morning, Swarali walks round the edge of a circular field having a radius of 100 meters. As shown in figure, if she starts from the point A and takes one round, how much distance has she walked and what is her displacement? 2. If a car starting from point P goes to point Q and then returns to point P, how much distance has it travelled and what is its displacement? Even if the displacement of an object is 0, the actual distance traversed by it may not be 0. Speed and velocity. Can you recall? 1. What are vectors and scalars? 2. Which of the quantities distance, speed, velocity, time, and displacement are scalars and which are vectors? Speed is equal to total distance travelled upon time required. The distance travelled in a particular direction by an object in unit time is called its velocity. Here, unit time can be 1 second, 1 minute, 1 hour, etc. If large units are used, 1 year can also be used as a unit of time. The displacement that occurs in unit time is called velocity. Velocity is equal to displacement upon time. Always remember: 1. The units of speed and velocity are the same. In the SI system, the unit is meter per second, while in the CGS system it is centimeter per second. 2. Speed is related to distance, while velocity is related to the displacement. 3. If the motion is along a straight line, the values of speed and velocity are the same. Otherwise, they can be different. Velocity is the displacement that occurs in unit time. In the first example, the straight line distance between the houses of Sheetal and Sangeeta is 500 meters, and that between Sangeeta's house and the school is 1200 meters. Also, the straight line distance between Sheetal's house and the school is 1300 meters. Suppose Sheetal takes 5 minutes to reach Sangeeta's house and then 24 minutes to reach the school from there. Then, Sheetal's speed along path A is equal to distance upon time, which is equal to 500 meters upon 5 minutes, which is equal to 100 meters per minute. Sheetal's speed along path B is equal to distance upon time, which is equal to 1200 meters upon 24 minutes, which is equal to 50 meters per minute. Sheetal's average speed is equal to total distance upon total time, which is equal to 1700 meters upon 29 minutes, which is equal to 58.6 meters per minute. Sheetal's velocity is equal to displacement upon time, which is equal to 1300 meters upon 29 minutes. Sheetal's velocity is equal to 44.83 meters per minute. Effect of speed and direction on velocity. Sachin is travelling on a motorbike. Explain what will happen in the following events during Sachin's ride. 1. What will be the effect on the velocity of the motorcycle if its speed increases or decreases, but its direction remains unchanged? 2. In case of a turning on the road, will the velocity and speed be the same? If Sachin changes the direction of the motorcycle, keeping its speed constant, what will be the effect on the velocity? 3. If on a turning, Sachin changes the direction as well as the speed of the motorcycle, what will be the effect on its velocity? It is clear from the above that velocity depends on speed as well as direction, and that velocity changes by 1. Changing the speed while keeping the direction same. 2. Changing the direction while keeping the speed same. 3. Changing the speed as well as the direction. Always remember, the first scientist to measure speed as the distance upon time was Galileo. The speed of sound in dry air is 343.2 meters per second, while the speed of light is about 3 multiplied by 10 raised to 8 meters per second. The speed of revolution of the Earth around the Sun is about 29,770 meters per second. Uniform and non-uniform linear motion. Amar, Akbar and Anthony are traveling in different cars with different velocities. The distances covered by them during different time intervals are given in the following table. Time in the clock 5. Distance covered by Amar in kilometers 0. Distance covered by Akbar in kilometers 0. Distance covered by Anthony in kilometers 0. Time in the clock 5:30. Distance covered by Amar in kilometers 20. Distance covered by Akbar in kilometers 18. Distance covered by Anthony in kilometers 14. Time in the clock 6. Distance covered by Amar in kilometers 40. Distance covered by Akbar in kilometers 36. Distance covered by Anthony in kilometers 28. Time in the clock 6:30. Distance covered by Amar in kilometers 60. Distance covered by Akbar in kilometers 42. Distance covered by Anthony in kilometers 42. Time in the clock 7. Distance covered by Amar in kilometers 80. Distance covered by Akbar in kilometers 70. Distance covered by Anthony in kilometers 56. Time in the clock 7:30. Distance covered by Amar in kilometers 100. Distance covered by Akbar in kilometers 95. Distance covered by Anthony in kilometers 70. Time in the clock 8. Distance covered by Amar in kilometers 120. Distance covered by Akbar in kilometers 120. Distance covered by Anthony in kilometers 84. Use your brain power. 1. What is the time interval between the notings of distances made by Amar, Akbar and Anthony? 2. Who has covered equal distances in equal time intervals? 3. Are all the distances covered by Akbar in the fixed time intervals the same? 4. Considering the distances covered by Amar, Akbar and Anthony in fixed time intervals, what can you say about their speeds? If an object covers equal distances in equal time intervals, it is said to be moving with uniform speed. If an object covers unequal distances in equal time intervals, it is said to be moving with non-uniform speed. For example, the motion of a vehicle being driven through heavy traffic. Acceleration. Let's try this. 1. Take a 1 meter long plastic tube and cut it lengthwise into 2 halves. 2. Take one of the channel-shaped pieces. Place one of its ends on the ground and hold the other at some height from the ground as shown in figure 3. Take a small ball and release it from the upper end of the channel. 4. Observe the velocity of the ball as it rolls down along the channel. 5. Is its velocity the same at all points? 6. Observe how the velocity changes as it moves from the top through the middle and to the bottom. You must have all played on a slide in a park. You know that while sliding down, the velocity is less at the top, it increases in the middle and becomes 0 towards the end. The rate of change of velocity is called acceleration. Acceleration is equal to change in velocity upon time. If the initial velocity is u and in time t it changes to the final velocity v, acceleration is equal to a equal to final velocity minus initial velocity upon time. Therefore, a is equal to v minus u upon t. If the velocity of an object changes during a certain time period, then it is said to have accelerated motion. An object in motion can have two types of acceleration. 1. If the velocity changes by equal amounts in equal time intervals, the object is said to be in uniform acceleration. 2. If the velocity changes by unequal amounts in equal time intervals, the object is said to be non-uniform acceleration. Use your brain power. 1. When an object is at rest in the beginning of its motion, what is its initial velocity? 2. When an object comes to rest at the end of its motion, what is its final velocity? Positive, negative, and zero acceleration. An object can have positive or negative acceleration. When the velocity of an object increases, the acceleration is positive. In this case, the acceleration is in the direction of the velocity. When the velocity of an object decreases with time, it has negative acceleration. Negative acceleration is also called deceleration. Its direction is opposite to the direction of velocity. If the velocity of the object does not change with time, it has zero acceleration. Distance-time graph for uniform motion. The following table shows the distances covered by a car in fixed time intervals. Draw a graph of distance against time, taking time along the x-axis and distance along the y-axis in figure. Time in seconds, 0. Distance in meters, 0. Time in seconds, 10. Distance in meters, 15. Time in seconds, 20. Distance in meters, 30. Time in seconds, 30. Distance in meters, 45. Time in seconds, 40. Distance in meters, 60. Time in seconds, 50. Distance in meters, 75. Time in seconds, 60. Distance in meters, 90. Time in seconds, 70. Distance in meters, 105. An object in uniform motion covers equal distances in equal time intervals. Thus, the graph between distance and time is a straight line. Use your brain power. In the distance-time graph above, what does the slope of the straight line indicate? Distance-time graph for non-uniform motion. The following table shows the distances covered by a bus in equal time intervals. Draw a graph of distance against time, taking the time along the x-axis and distance along the y-axis. Does the graph show a direct proportionality between distance and time? Time in seconds, 0. Distance in meters, 0. Time in seconds, 5. Distance in meters, 7. Time in seconds, 10. Distance in meters, 12. Time in seconds, 15. Distance in meters, 20. Time in seconds, 20. Distance in meters, 30. Time in seconds, 25. Distance in meters, 41. Time in seconds, 30. Distance in meters, 50. Time in seconds, 35. Distance in meters, 58. Here, the distance changes non-uniformly with time. Thus, the bus is having non-uniform motion. Use your brain power. What difference do you see in the distance-time graphs for uniform and non-uniform motion? Velocity-time graph for uniform velocity. A train is moving with a uniform velocity of 60 km per hour for 5 hours. The velocity-time graph for this uniform motion is shown in figure 1. With the help of the graph, how will you determine the distance covered by the train between 2 and 4 hours? 2. Is there a relation between the distance covered by the train between 2 and 4 hours and the area of a particular quadrangle in the graph? What is the acceleration of the train? Velocity-time graph for uniform acceleration. The changes in the velocity of a car in specific time intervals are given in the following table. Time in seconds, 0. Velocity, meter per seconds, 0. Time in seconds, 5. Velocity in meter per seconds, 8. Time in seconds, 10. Velocity in meter per seconds, 16. Time in seconds, 15. Velocity in meter per seconds, 24. Time in seconds, 20. Velocity in meter per seconds, 32. Time in seconds, 25. Velocity in meter per seconds, 40. Time in seconds, 30. Velocity in meter per seconds, 48. Time in seconds, 35. Velocity in meter per seconds, 56. The velocity-time graph in figure shows that 1. The velocity changes by equal amounts in equal time intervals. Thus, this is uniformly accelerated motion. How much does the velocity change every 5 minutes? 2. For all uniformly accelerated motions, the velocity-time graph is a straight line. 3. For non-uniformly accelerated motions, the velocity-time graph may have any shape depending on how the acceleration changes with time. From the graph, we can determine the distance covered by the car between the 10th and the 20th seconds, as we did in the case of the train in the previous example. The difference is that the velocity of the car is not constant, unlike that of the train, but is continuously changing because of uniform acceleration. In such a case, we have to use the average velocity of the car in the given time interval to determine the distance covered in that interval. From the graph, the average velocity of the car is equal to 32 plus 16 upon 2, which is equal to 24 meters per second. Multiplying this by the time interval, that is 10 seconds, gives us the distance covered by the car. Distance covered is equal to 24 meters per second multiplied by 10 seconds, which is equal to 240 meters. Check that, similar to the example of the train, the distance covered is given by the area of quadrangle ABCD. Area of square ABCD is equal to area of square AECD plus area of triangle ABE. Equations of motion using graphical method. Newton studied motion of an object and gave a set of 3 equations of motion. These relate the displacement, velocity, acceleration and time of an object moving along a straight line. Suppose an object is in motion along a straight line with initial velocity u. It attains a final velocity v in time t due to acceleration a. Its displacement is s. The 3 equations of motion can be written as v is equal to u plus at. This is the relation between velocity and time. S is equal to ut plus 1 upon 2 at square. This is the relation between displacement and time. V square is equal to u square plus 2as. This is the relation between displacement and velocity. Let us try to obtain these equations by the graphical method. Equation describing the relation between velocity and time. Figure shows the change in velocity with time of a uniformly accelerated object. The object starts from the point D in the graph with velocity u. Its velocity keeps increasing and after time t, it reaches the point B on the graph. The initial velocity of the object is equal to u, which is equal to OD. The final velocity of the object is equal to v, which is equal to OC. Time is equal to t, which is equal to OE. Acceleration a is equal to change in velocity upon time, which is equal to final velocity minus initial velocity upon time, which is equal to OC minus OD upon t. Therefore, CD is equal to AT1. OC minus OD is equal to CD. Draw a line parallel to the y-axis passing through B. This will cross the x-axis in E. Draw a line parallel to the x-axis passing through D. This will cross the line BE at A. From the graph, BE is equal to AB plus AE. Therefore, V is equal to CD plus OD. AB is equal to CD and AE is equal to OD. Therefore, V is equal to AT plus U from 1. Therefore, V is equal to U plus AT. This is the first equation of motion. Equation describing the relation between displacement and time. Let us suppose that an object is in uniform acceleration a and it has covered the distance s within time t. From the graph, the distance covered by the object during time t is given by the area of quadrangle DOEB. Therefore, S is equal to area of quadrangle DOEB, which is equal to area of rectangle DOEA plus area of triangle DAB. Therefore, S is equal to AE multiplied by OE plus 1 upon 2 into AB into DA. But AE is equal to U, OE is equal to T, and OE is equal to DA, which is equal to T. AB is equal to AT, AB is equal to CD from 1. Therefore, S is equal to U multiplied by T plus 1 upon 2 multiplied by AT multiplied by T. Therefore, Newton's second equation of motion is S is equal to UT plus 1 upon 2 AT square. Equation describing the relation between displacement and velocity. We have seen that from the graph in figure, we can determine the distance covered by the object in time t from the area of the quadrangle DOEB. DOEB is a trapezium, so we can use the formula for its area. Therefore, S is equal to area of trapezium DOEB. Therefore, S is equal to 1 upon 2 multiplied by sum of lengths of parallel sides multiplied by distance between the parallel sides. Therefore, S is equal to 1 upon 2 multiplied by OD plus BE multiplied by OE, but OD is equal to U, BE is equal to V, and OE is equal to T. Therefore, S is equal to 1 upon 2 multiplied by U plus V multiplied by T. But A is equal to V minus U upon T. Therefore, T is equal to V minus U upon A. Therefore, S is equal to 1 upon 2 multiplied by U plus V multiplied by V minus U upon A. Therefore, S is equal to V plus U, V minus U upon 2A. Therefore, 2AS is equal to V plus U, V minus U, which is equal to V square minus U square. Therefore, V square is equal to U square plus 2AS. This is Newton's third equation of motion. Always remember, the velocity of an accelerated object changes with time. Change in the velocity can be due to a change in direction or magnitude of the velocity or both. Uniform circular motion. Let's try this. Observe the tip of the second hand of a clock. What can you say about its velocity and speed? The speed of the tip is constant, but the direction of its displacement and therefore its velocity is constantly changing. As the tip is moving along a circular path, its motion is called uniform circular motion. Can you give more examples of such motion? Try out and think about it. 1. Draw a rectangular path. 2. Place the tip of your pencil on the middle of any side of the square path and trace the path. 3. Note how many times you have to change the direction while tracing the complete path. 4. Now, repeat this action for a pentagonal, hexagonal, octagonal path and Note the number of times you have to change direction. 5. If you increase the number of sides of the polygon and make it infinite, how many times will you have to change the direction? What will be the shape of the path? This shows that as we increase the number of sides, we have to keep changing the direction more and more times. And when we increase the number of sides to infinity, the polygon becomes a circle. When an object is moving with a constant speed along a circular path, the change in velocity is only due to the change in direction. Hence, it is accelerated motion. When an object moves with constant speed along a circular path, the motion is called uniform circular motion. Example, the motion of a stone in a sling or that of any point on a bicycle wheel when they are in uniform motion. If an object moving along a circular path of radius r takes time t to come back to its starting position, its speed can be determined using the formula given below. Speed is equal to circumference upon time. V is equal to 2 pi r upon t. R is equal to radius of the circle. Research. Find out more examples of circular motion in day-to-day life. Determining the direction of velocity in uniform circular motion. Let's try this. Take a circular disc and put a 5 rupee coin at a point along its edge. Make it move around its axis by putting a pin through it. When the disc is moved at higher speed, the coin will be thrown off as shown. Note the direction in which it is thrown off. Repeat the action, placing the coin at different points along the edge of the circle and observe the direction in which the coin is thrown off. The coin will be thrown off in the direction of the tangent, which is perpendicular to the radius of disc. Thus, the direction in which it gets thrown off depends on its position at the moment of getting thrown off. It means that as the coin moves along a circular path, the direction of its motion is changing at every point. Solved examples. Example 1. An athlete is running on a circular track. He runs a distance of 400 meters in 25 seconds before returning to his original position. What is his average speed and velocity? Given. Total distance travelled is equal to 400 meters. Total displacement is equal to 0 as he returns to his original position. Total time is equal to 25 seconds. Average speed is equal to how much? Average velocity is equal to how much? Average speed is equal to total distance covered upon total time taken, which is equal to 400 upon 25, which is equal to 16 meters per second. Average velocity is equal to total displacement upon total time taken, which is equal to 0 upon 25, which is equal to 0 meters per second. Example 2. An aeroplane taxis on the runway for 30 seconds with an acceleration of 3.2 meter per second square before taking off. How much distance would it have covered on the runway? Given A is equal to 3.2 meter per second square, T is equal to 30 seconds, U is equal to 0, S is equal to how much? S is equal to ut plus 1 upon 2 at square, which is equal to 0 multiplied by 30 plus 1 upon 2 multiplied by 3.2 multiplied by 30 square, which is equal to 1440 meters. Example 3. A kangaroo can jump 2.5 meters vertically. What must be the initial velocity of the kangaroo? Given A is equal to 9.8 meter per second square, S is equal to 2.5 meters, V is equal to 0, U is equal to question mark, V square is equal to U square plus 2AS, 0 square is equal to U square plus 2 multiplied by minus 9.8, 2.5, negative sign is used as the acceleration is in the direction opposite to that of velocity. 0 is equal to U square minus 49, U square is equal to 49, U is equal to 7 meters per second. Example 4. A motorboat starts from rest and moves with uniform acceleration. If it attains the velocity of 15 meters per second in 5 seconds, calculate the acceleration and the distance travelled in that time. Given initial velocity u is equal to 0, final velocity v is equal to 15 meters per second, time t is equal to 5 seconds, acceleration is equal to a, which is equal to how much? From the first equation of motion, a is equal to v minus u upon t, which is equal to 15 minus 0 upon 5, which is equal to 3 meter per second square. From the second equation of motion, the distance covered will be S is equal to ut plus 1 upon 2 at square. S is equal to 0 multiplied by 5 plus 1 upon 2, 3 multiplied by 5 square, which is equal to 0 plus 75 upon 2, which is equal to 37.5 meters. Newton's laws of motion. What could be the reason for the following? 1. A static object does not move without the application of a force. 2. The force which is sufficient to lift a book from a table is not sufficient to lift the table. 3. Fruits on a tree fall down when its branches are shaken. 4. An electric fan keeps on rotating for some time even after it is switched off. If we look for reasons for the above, we realize that objects have some inertia. We have learned that inertia is related to the mass of the object. Newton's first law of motion describes this very property and is therefore also called the law of inertia. All instances of inertia are examples of Newton's first law of motion. Newton's first law of motion. Let's try this. Fill a glass with sand. Keep a piece of cardboard on it. Keep a 5 rupee coin on the cardboard. Now, strike the cardboard hard using your fingers. Observe what happens. Balanced and unbalanced force. You must have played tug-of-war. So long as the forces applied by both the sides are equal, that is, balanced, the center of the rope is static in spite of the applied forces. On the other hand, when the applied forces become unequal, that is, unbalanced, a net force gets applied in the direction of the greater force and the center of the rope shifts in that direction. An object continues to remain at rest or in a state of uniform motion along a straight line unless an external unbalanced force acts on it. When an object is at rest or in uniform motion along a straight line, it does not mean that no force is acting on it. Actually, there are a number of forces acting on it, but they cancel one another so that the net force is zero. Newton's first law explains the phenomenon of inertia, that is, the inability of an object to change its state of motion on its own. It also explains the unbalanced forces which cause a change in the state of an object at rest or in uniform motion. Newton's second law of motion. Let's try this. A. 1. Ask your friend to drop one plastic and one rubber ball from the same height. 2. You catch the balls. Which ball was easier to catch and why? B. 1. Ask your friend to throw a ball towards you at slow speed. Try to catch it. 2. Now ask your friend to throw the same ball at high speed towards you. Try to catch it. Which ball could you catch with greater ease? Why? The effect of one object striking another object depends both on the mass of the former object and its velocity. This means that the effect of the force depends on a property related to both mass and velocity of the striking object. This property was termed momentum by Newton. Momentum has magnitude as well as direction. Its direction is the same as that of velocity. In SI system, the unit of momentum is kilogram meters per second, while in CGS system, it is grams centimeters per second. If an unbalanced force applied on an object causes a change in the velocity of the object, then it also causes a change in its momentum. The force necessary to cause a change in the momentum of an object depends upon the rate of change of momentum. Momentum P. Momentum is the product of mass and velocity of an object. P is equal to mv. Momentum is a vector quantity. The rate of change of momentum is proportional to the applied force, and the change of momentum occurs in the direction of the force. Suppose an object of mass m has an initial velocity u. When a force F is applied in the direction of its velocity for time t, its velocity becomes v. Therefore, the initial momentum of the object is equal to mu. Its final momentum after time t is equal to mv. Therefore, rate of change of momentum is equal to change in momentum upon time. Therefore, rate of change of momentum is equal to mv minus mu upon t, which is equal to mv minus u upon t, which is equal to ma. According to Newton's second law of motion, the rate of change of momentum is proportional to the applied force. Therefore, ma is directly proportional to F. Therefore, F is equal to kma, where k is equal to constant of proportionality and its value is 1. F is equal to m multiplied by a. Consider two objects having different masses which are initially at rest. The initial momentum for both is 0. Suppose a force F acts for time t on both objects. The lighter object starts moving faster than the heavier object. However, from the above formula, we know that the rate of change of momentum, that is, F, in both objects is the same and the total change in their momentum will also be same, that is, Ft. Thus, if the same force is applied on different objects, the change in momentum is the same. In SI system, the unit of force is Newton. Newton, N, the force necessary to cause an acceleration of 1 meter per second square in an object of mass 1 kilogram is called 1 Newton. 1 Newton is equal to 1 kilogram multiplied by 1 meter per second square. In CGS system, the unit of force is a dyne. Dyne, the force necessary to cause an acceleration of 1 centimeter per second square in an object of mass 1 gram is called 1 dyne. 1 dyne is equal to 1 gram multiplied by 1 centimeter per second square. Use your brain power. Why is there a thick bed of sand for a high jumper to fall on after his jump? Newton's third law of motion. Let's try this. 1. Take a plastic boat and make a hole at its rear end. 2. Inflate a balloon and fix it on the hole in the boat. Release the boat in water. What happens to the boat as the air in the balloon escapes slowly? Why? We have learnt about force and its effect on an object through Newton's first and second laws of motion. However, in nature, force cannot act alone. Force is a reciprocal action between two objects. Forces are always applied in pairs. When one object applies a force on another object, the latter object also simultaneously applies a force on the former object. The forces between two objects are always equal and opposite. This idea is expressed in Newton's third law of motion. The force applied by the first object is called action force, while the force applied by the second object on the first is called reaction force. Every action force has an equal and opposite reaction force which acts simultaneously. 1. Action and reaction are terms that express force. 2. These forces act in pairs. One force cannot exist by itself. 3. Action and reaction forces act simultaneously. 4. Action and reaction forces act on different objects. They do not act on the same object and hence cannot cancel each other's effect. Use your brain power. 1. While hitting a ball with a bat, the speed of the bat decreases. 2. A gun recoils, that is, moves backwards when a bullet is fired. 3. Mechanism of firing of a rocket. How will you explain these with the help of Newton's third law of motion? Of conservation of momentum. Suppose an object A has mass m1 and its initial velocity is u1. An object B has mass m2 and initial velocity u2. According to the formula for momentum, the initial momentum of A is m1 u1 and that of B is m2 u2. Suppose these two objects collide. Let the force on A due to B be F1. This force will cause acceleration in A and its velocity will become v1. Therefore, momentum of A after collision is equal to m1 v1. According to Newton's third law of motion, A also exerts an equal force on B, but in the opposite direction. This will cause a change in the momentum of B. If its velocity after collision is v2, the momentum of B after collision is m2 v2. If F2 is the force that acts on object B, F2 is equal to minus F1. Therefore, m2a2 is equal to minus m1a1 because F is equal to ma. Therefore, m2 multiplied by v2 minus u2 upon t is equal to minus m1 multiplied by v1 minus u1 upon t because A is equal to v minus u upon t. Therefore, m2 v2 minus u2 is equal to minus m1 v1 minus u1. Therefore, m2 v2 minus m2 u2 is equal to minus m1 v1 plus m1 u1. Therefore, m2 v2 plus m1 v1 is equal to m1 u1 plus m2 u2. The magnitude of total final momentum is equal to the magnitude of total initial momentum. Thus, if no external force is acting on two objects, then their total initial momentum is equal to their total final momentum. This statement is true for any number of objects. When no external force acts on two interacting objects, their total momentum remains constant. It does not change. This is a corollary to Newton's third law of motion. The momentum is unchanged after the collision. The momentum gets redistributed between the colliding objects. The momentum of one of the objects decreases while that of the other increases. Thus, we can also state this corollary as follows. When two objects collide, the total momentum before collision is equal to the total momentum after collision. In order to understand this principle, let us consider the example of a bullet fired from a gun. When a bullet of mass m1 is fired from a gun of mass m2, its velocity becomes v1 and its momentum becomes m1 v1. Before firing the bullet, both the gun and the bullet are at rest and hence the total initial momentum is 0. According to the above law, the total final momentum also has to be 0. Thus, the forward-moving bullet causes the gun to move backward after firing. This backward motion of the gun is called its recoil. The velocity of recoil, v2, is such that m1 v1 plus m2 v2 is equal to 0 or v2 is equal to minus m1 upon m2 multiplied by v1. As the mass of the gun is much higher than the mass of the bullet, the velocity of the gun is much smaller than the velocity of the bullet. The magnitude of the momentum of the bullet and that of the gun are equal and their directions are opposite. Thus, the total momentum is constant. Total momentum is also constant during the launch of a rocket. Solved examples. Example 1. The mass of a cannon is 500 kilograms and it recoils with a speed of 0.25 meters per second. What is the momentum of the cannon? Given, mass of the cannon is equal to 500 kilograms, recoil speed is equal to 0.25 meters per second, momentum is equal to how much? Momentum is equal to m multiplied by v, which is equal to 500 multiplied by 0.25, which is equal to 125 kilograms meter per second. Example 2. Two balls have masses of 50 grams and 100 grams and they are moving along the same line in the same direction with velocities of 3 meters per second and 1.5 meters per second respectively. They collide with each other and after the collision, the first ball moves with a velocity of 2.5 meters per second. Calculate the velocity of the other ball after collision. Given, the mass of the first ball is equal to m1, which is equal to 50 grams, which is equal to 0.05 kilograms. Mass of the second ball is equal to m2, which is equal to 100 grams, which is equal to 0.1 kilograms. Initial velocity of the first ball is equal to u1, which is equal to 3 meters per second. Initial velocity of the second ball is equal to u2, which is equal to 1.5 meters per second. Final velocity of the first ball is equal to v1, which is equal to 2.5 meters per second. Final velocity of the second ball is equal to v2, which is equal to how much? According to the law of conservation of momentum, total initial momentum is equal to total final momentum. m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. 0.05 multiplied by 3 plus 0.1 multiplied by 1.5 is equal to 0.05 multiplied by 2.5 plus 0.1 multiplied by v2. Therefore, 0.15 plus 0.15 is equal to 0.125 plus 0.1 v2. Therefore, 0.3 is equal to 0.125 plus 0.1 v2. Therefore, 0.1 v2 is equal to 0.3 minus 0.125. Therefore, v2 is equal to 0.175 upon 0.1, which is equal to 1.75 meters per second.